Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Commerford Martin. Appendix 10. Edison's Dynamo Work. At the present writing, when, after the phenomenally rapid electrical development of 30 years, we find on the market a great variety of modern forms of efficient current generators, advertised under the names of different inventors, none, however, bearing the name of Edison, a young electrical engineer of the present generation might well inquire whether the great inventor had ever contributed anything to the art beyond a mere type of machine formerly made and bearing his name, but not now marketed except second hand. For adequate information he might search in vain the books usually regarded as authorities on the subject of dynamo electric machinery, for with slight exceptions there has been a singular unanimity in the omission of writers to give Edison credit for his great and basic contributions to heavy current technics, although they have been universally acknowledged by scientific and practical men to have laid the foundation for the efficiency of and to be embodied in all modern generators of current. It might naturally be expected that the essential facts of Edison's work would appear on the surface of his numerous patents of dynamo electric machinery, but such is not necessarily the case, unless they were carefully studied in the light of the state of the art as it existed at the time. While some of these patents, especially the earlier ones, cover specific devices embodying fundamental principles that not only survive to the present day, but actually lie at the foundation of the art as it now exists, there is no revelation therein of Edison's preceding studies of magnets, which extended over many years, nor of his later systematic investigations and deductions. Dynamo electric machines of a primitive kind have been invented and were in use to a very limited extent for arc lighting and electroplating for some years prior to the summer of 1819, when Edison, with an embryonic lighting system in mind, cast about for a type of machine technically and commercially suitable for the successful carrying out of his plans. He found absolutely none. On the contrary, all of the few types then obtainable were uneconomical, indeed wasteful, in regard to efficiency. The art, if indeed there can be said to have been an art at that time, was in chaotic confusion, and only because of Edison's many years' study of the magnet was he enabled to conclude that insufficiency in quantity of iron in the magnets of such machines, together with poor surface contacts, rendered the cost of magnetization abnormally high. The heating of solid armatures, the only kind then known, and poor insulation in the commutators also gave rise to serious losses. But perhaps the most serious drawback lay in the high resistance armature, based upon the highest scientific dictum of the time, that in order to obtain the maximum amount of work from a machine, the internal resistance of the armature must equal the resistance of the exterior circuit, although the application of this principle entailed the useless expenditure of at least 50% of the applied energy. It seems almost incredible that a little over 30 years ago the sum of scientific knowledge in regard to dynamo electric machines was so meagre that the experts of the period should settle upon such a dictum as this, but such was the fact, as will presently appear. Mechanical generators of electricity were comparatively new at that time. Their theory and practice were very imperfectly understood. Indeed, it is quite within the bounds of truth to say that the correct principles were befogged by reason of the lack of practical knowledge of their actual use. Electricians and scientists of the period have been accustomed for many years past to look to the chemical battery as the source from which to obtain electrical energy, and in the practical application of such energy to telegraphy and kindred uses, much thought and ingenuity had been expended in studying combinations of connecting such cells so as to get the best results. In the textbooks of the period it was stated as a settled principle that in order to obtain the maximum work out of a set of batteries, the internal resistance must approximately equal the resistance of the exterior circuit. This principle and its application in practice were quite correct as regards chemical batteries, but not as regards dynamo machines. Both were generators of electrical current, but so different in construction and operation that rules applicable to the practical use of the one did not apply with proper commercial efficiency to the other. At the period under consideration, which may be said to have been just before dawn of the day of electric light, the philosophy of the dynamo had been seen only in mysterious, hazy outlines, just emerging from the darkness of departing night. Perhaps it is not surprising, then, that the dynamo was loosely regarded by electricians as the practical equivalent of a chemical battery, that many of the characteristics of performance of the chemical cell were also attributed to it, and that if the maximum work could be gotten out of a set of batteries when the internal and external resistances were equal, and this was commercially the best thing to do, so must it also be with a dynamo. It was by no miracle that Edison was far and away ahead of his time when he undertook to improve the dynamo. He possessed of absolute knowledge far beyond that of his contemporaries. This he had acquired by the hardest kind of work and incessant experimentation with magnets of all kinds during several years preceding, particularly in connection with his study of automatic telegraphy. His knowledge of magnets was tremendous. He had studied and experimented with electromagnets in enormous variety, and knew their peculiarities in charge and discharge, lag, self-induction, static effects, condenser effects, and various other phenomena connected therewith. He had also made collateral studies of iron, steel, copper, insulation, winding, etc. Hence, by reason of this extensive work and knowledge, Edison was naturally in a position to realize the utter commercial impossibility of the then best dynamo machine in existence, which had an efficiency of only 40% and was constructed on the cut and try principle. He was also naturally in a position to assume the task he set out to accomplish, of undertaking to plan and build an improved type of machine that should be commercial in having an efficiency of at least 90%. Truly a prodigious undertaking in those dark days, when from the standpoint of Edison's large experience, the most practical and correct electrical treatise was contained in the Encyclopaedia Britannica, and in a German publication which Mr. Upton had brought with him after he had finished his studies with the illustrious Helmholtz. It was at this period that Mr. Upton commenced his association with Edison, bringing to the great work the very latest scientific views and the assistance of the higher mathematics, to which he had devoted his attention for several years previously. As some account of Edison's investigations in this connection has already been made in Chapter 12 of the narrative, we shall not enlarge upon them here, but quote from An Historical Review by Charles L. Clark, Laboratory Assistant at Menlo Park, 1880–81, Chief Engineer of the Edison Electric Light Company, 1881–84. In June, 1879, was published the account of the Edison dynamo electric machine that survived in the art. This machine went into extensive commercial use, and was notable for its very massive and powerful field magnets, an armature of extremely low resistance as compared with the combined external resistance of the supply mains and lamps. By means of the large masses of iron in the field magnets, and closely fitted joints between the several parts thereof, the magnetic reluctance of the iron parts of the magnetic circuit was reduced to a minimum, and the required magnetization effected with the maximum economy. At the same time Mr. Edison announced the commercial necessity of having the armature of the dynamo of low resistance, as compared with the external resistance, in order that a large percentage of the electrical energy developed should be utilized in the lamps, and only a small percentage lost in the armature, albeit this procedure reduced the total generating capacity of the machine. He also proposed to make the resistance of the supply mains small, as compared with the combined resistance of the lamps in multiple arc, in order to still further increase the percentage of energy utilized in the lamps. And likewise to this end, the combined resistance of the generator armatures in multiple arc was kept relatively small by adjusting the number of generators operating in multiple at any time to the number of lamps then in use. The field magnet circuits of the dynamos were connected in multiple with a separate energizing source, and the field current and strength of field were regulated to maintain the required amount of electromotive force upon the supply mains under all conditions of load, from the maximum to the minimum number of lamps in use, and to keep the electromotive force of all machines alike. Among the earliest of Edison's dynamo experiments were those relating to the core of the armature. He realized at once that the heat generated in a solid core was a prolific source of loss. He experimented with bundles of iron wires variously insulated, also with sheet iron rolled cylindrically and covered with iron wire wound concentrically. These experiments and many others were tried in a great variety of ways, until, as the result of all this work, Edison arrived at the principle which has remained in the art to this day. He split up the iron core of the armature into thin laminations, separated by paper, thus practically suppressing Foucault currents therein and resulting heating effect. It was in his machine also that mica was used for the first time as an insulating medium in a commutator. Footnote. The commercial manufacture of built-up sheets of mica for electrical purposes was first established at the Edison Machine Works, Gourk Street, New York, in 1881. End footnote. Elementary as these principles will appear to the modern student or engineer, they were denounced as nothing short of absurdity at the time of their promulgation, especially so with regard to Edison's proposal to upset the then settled dictum that the armature resistance should be equal to the external resistance. His proposition was derided in the technical press of the period, both at home and abroad. As public opinion can be best illustrated by actual quotation, we shall present a characteristic instance. In the Scientific American of October 18, 1879, there appeared an illustrated article by Mr. Upton on Edison's dynamo machine, in which Edison's views and claims were set forth. A subsequent issue contained a somewhat acrimonious letter of criticism by a well-known maker of dynamo machines. At the risk of being lengthy, we must quote nearly all this letter. I can scarcely conceive it as possible that the article on the above subject, Edison's electric generator, in last week's Scientific American, could have been written from statements derived from Mr. Edison himself, inasmuch as so many of the advantages claimed for the machine described, and statements of the results obtained, were so manifestly absurd as to indicate on the part of both writer and prompter a positive want of knowledge of the electric circuit and the principles governing the construction and operation of electric machines. It is not my intention to criticize the design or construction of the machine, not because they are not open to criticism, as I am now and have been for many years engaged in the manufacture of electric machines, but rather to call attention to the impossibility of obtaining the described results without destroying the doctrine of the conservation and correlation of forces. It is stated that the internal resistance of the armature of this machine is only 1/2 ohm. On this fact, and the disproportion between this resistance and that of the external circuit, the theory of the alleged efficiency of the machine is stated to be based, for we are informed that, while this generator in general principle is the same as in the best well-known forms, still there is an all-important difference, which is that it will convert and deliver for useful work nearly double the number of foot-pounds that any other machine will under like conditions. The writer of this critical letter then proceeds to quote Mr. Upton's statement of this efficiency. Now the energy converted is distributed over the whole resistance; hence, if the resistance of the machine be represented by 1, and the exterior circuit by 9, then of the total energy converted, 9/10 will be useful, as it is outside of the machine, and 1/10 is lost in the resistance of the machine. After this, the critic goes on to say, how anyone acquainted with the laws of the electric circuit can make such statements is what I cannot understand. The statement last quoted is mathematically absurd. It implies either that the machine is capable of increasing its own electromotive forces 9 times without an increased expenditure of power, or that external resistance is not resistance to the current induced in the Edison machine. Does Mr. Edison, or anyone for him, mean to say that little r divided by n enables him to obtain n times E, and that C is not equal to E divided by the quantity of little r divided by n plus big R? If so, Mr. Edison has discovered something more than perpetual motion, and Mr. Keeley had better retire from the field. Further on the writer, Mr. Upton, gives us another example of this mode of reasoning, when emboldened and satisfied with the absurd theory above exposed, he endeavors to prove the cause of the inefficiency of the Siemens and other machines. Couldn't the writer of the article see that since C equals E divided by the quantity of little r plus big R, that by big R divided by n, or by making big R equal little r, the machine would, according to his theory, have returned more useful current to the circuit than could be due to the power employed, and in the ratio indicated, so that there would actually be a creation of force. In conclusion, allow me to say that if Mr. Edison thinks he has accomplished so much by the reduction of the internal resistance of his machine, that he has much more to do in this direction before his machine will equal in this respect others already in the market. Another participant in the controversy on Edison's generator was a scientific gentleman, who in a long article published in the Scientific American in November, 1879, gravely undertook to instruct Edison in the ABC of electrical principles, and then proceeded to demonstrate mathematically the impossibility of doing what Edison had actually done. This critic concludes with a gentle rebuke to the inventor for ill-timed jesting, and a suggestion to furnish authentic information. In the light of facts, as they were and are, this article is so full of humor that we shall indulge in a few quotations. It commences in ABC fashion as follows: Electrical machines convert mechanical into electrical energy. The ratio of yield to consumption is the expression of the efficiency of the machine. How many foot-pounds of electricity can be got out of 100 foot-pounds of mechanical energy? Certainly not more than 100. Certainly less. The facts and laws of physics, with the assistance of mathematical logic, never fail to furnish precious answers to such questions. The would-be critic then goes on to tabulate tests of certain other dynamo machines by a committee of the Franklin Institute in 1879, the results of which showed that these machines returned about 50% of the applied mechanical energy, ingeniously remarking, "Why is it that when we have produced the electricity, half of it must slip away?" Some persons will be content if they are told simply that it is a way which electricity has of behaving. But there is a satisfactory, rational explanation which I believe can be made plain to persons of ordinary intelligence. It ought to be known to all those who are making or using machines. I am grieved to observe that many persons who talk and write glibly about electricity do not understand it; some even ignore or deny the fact to be explained. Here followed his explanation, after which he goes on to say, at this point plausibly comes in a suggestion that the internal part of the circuit be made very small and the external part very large. Why not, say, make the internal part 1 and the external 9, thus saving 9/10 and losing only 1/10? Unfortunately, this suggestion is not practical. A fallacy is concealed in it. He then goes on to prove his case mathematically, to his own satisfaction, following it sadly by condoling with, and a warning to Edison. But about Edison's electric generator. No one capable of making the improvements in the telegraph and telephone, for which we are indebted to Mr. Edison, could be other than an accomplished electrician. His reputation as a scientist, indeed, is besmirched by the newspaper exaggerations, and no doubt he will be more careful in future. But there is a danger nearer home, indeed in his very household. The writer of page 242 (the original article) is probably a friend of Mr. Edison, but possibly, alas, a wicked partner. Why does he say such things as these? Mr. Edison claims that he realizes 90% of the power applied to his machine in external work. Perhaps the writer is a humorist, and had in his mind Colonel Sanders, etc., which he could not keep out of a serious discussion. But such jests are not good. Mr. Edison has built a very interesting machine, and he has the opportunity of making a valuable contribution to the electrical arts by furnishing authentic accounts of its capabilities. The foregoing extracts are unavoidably lengthy, but viewed in the light of facts, serve to illustrate most clearly that Edison's conceptions and work were far and away ahead of the comprehension of his contemporaries in the art, and that his achievements in the line of efficient dynamo design and construction were indeed truly fundamental and revolutionary in character. Much more of similar nature to the above could be quoted from other articles published elsewhere, but the foregoing will serve as instances, generally representing all. In the controversy which appeared in the columns of the Scientific American, Mr. Upton, Edison's mathematician, took up the question on his side, and answered the critics by further elucidations of the principles on which Edison had founded such remarkable and radical improvements in the art. The type of Edison's first dynamo-electric machine, the description of which gave rise to the above controversy, is shown in Figure 1. Any account of Edison's work on the dynamo would be incomplete did it omit to relate his conception and construction of the great, direct-connected, steam-driven generator that was the prototype of the colossal units which are used throughout the world today. In the demonstrating plant installed and operated by him at Menlo Park in 1880, 10 dynamos of 8 horsepower each were driven by a slow-speed engine through a complicated system of countershafting, and to quote from Mr. Clark's Historical Review, it was found that a considerable percentage of the power of the engine was necessarily wasted in friction by this method of driving, and to prevent this waste, and thus increase the economy of his system, Mr. Edison conceived the idea of substituting a single large dynamo for the several small dynamos, and directly coupling it with the driving engine, and at the same time preserve the requisite high armature speed by using an engine of the high-speed type. He also expected to realize still further gains in economy from the use of a large dynamo in place of several small machines by a more than correspondingly lower armature resistance, less energy for magnetizing the field, and for other minor reasons. To the same end, he intended to supply steam to the engine under a much higher boiler pressure than was customary in stationary engine driving at that time. The construction of the first one of these large machines was commenced late in the year 1880. Early in 1881 it was completed and tested, but some radical defects in armature construction were developed, and it was also demonstrated that a rate of engine speed too high for continuously safe and economical operation had been chosen. The machine was laid aside. An accurate illustration of this machine, as it stood in the engine room at Menlo Park, is given in Van Nostrand's Engineering Magazine, volume 25, opposite page 439, and a brief description is given on page 450. With the experience thus gained, Edison began, in the spring of 1881, at the Edison Machine Works, Gork Street, New York City, the construction of the first successful machine of this type. This was the great machine known as Jumbo No. 1, which is referred to in the narrative as having been exhibited at the Paris International Electrical Exposition, where it was regarded as the wonder of the electrical world. An intimation of some of the tremendous difficulties encountered in the construction of this machine has already been given in preceding pages, hence we shall not now enlarge on the subject, except to note in passing that the terribly destructive effects of the spark of self-induction, and the arcing following it, were first manifested in this powerful machine, but were finally overcome by Edison after a strenuous application of his powers to the solution of the problem. It may be of interest, however, to mention some of its dimensions and electrical characteristics, quoting again from Mr. Clark. The field magnet has 8 solid cylindrical cores, 8 inches in diameter and 57 inches long. upon each of which was wound an exciting coil of 3.2 ohms resistance, consisting of 2,184 turns of No. 10 BWG insulated copper wire, disposed in 6 layers. The laminated iron core of the armature, formed of thin iron discs, was 33 3/4 inches long, and had an internal diameter of 12½ inches and an external diameter of 26 7/16 inches. It was mounted on a 6-inch shaft. The field poles are 33 3/4 inches long and 27½ inches inside diameter. The armature winding consisted of 146 copper bars on the face of the core, connected into a closed coil winding by means of 73 copper discs at each end of the core. The cross-sectional area of each bar was 0.2 square inch, their average length was 42.7 inches, and the copper end discs were 0.065 inches thick. The commutator had 73 sections. The armature resistance was 0.0092 ohm, of which 0.0055 ohm was in the armature bars and 0.0037 ohm in the end discs. An illustration of the next latest type of this machine is presented in Figure 2. Begin footnote. Had Edison, in Upton's Scientific American article, in 1879, proposed such an exceedingly low armature resistance for this immense generator, although its ratio was proportionate to the original machine, his critics might possibly have been sufficiently indignant as to be unable to express themselves coherently. End footnote. The student may find it interesting to look up Edison's United States patent numbers 242,898, 263,133, 263,146, and 246,647, bearing upon the construction of the jumbo; also illustrated articles in the technical journals of the time, among which may be mentioned Scientific American, Volume 45, page 367, Engineering, London, Volume 32, pages 409 and 419, the Telegraphic Journal and Electrical Review, London, Volume 9, pages 431 through 433 and 436 through 446, La Nature, Paris, 9th year, Part 2, pages 408 through 409, Zeitschrift für angewandte Elektrizitätslehre, Munich and Leipzig, Volume 4, pages 4 through 14, and Drudge's Electrical Illumination, 1882, Volume 1, page 261. The further development of these great machines later on, and their extensive practical use, are well known and need no further comment, except in passing it may be noted that subsequent machines had each a capacity of 1,200 lamps of 16-candle power, and that the armature resistance was still further reduced to 0.0039 ohm. Edison's clear insight into the future, as illustrated by his persistent advocacy of large direct connected generating machines, is abundantly vindicated by present-day practice. His jumbo machines of 175 horsepower, so enormous for their time, have served as prototypes, and have been succeeded by generators which have constantly grown in size and capacity, until at this time (1910) it is not uncommon to employ such generating units of a capacity of 14,000 kilowatts, or about 18,666 horsepower. We have not entered into specific descriptions of the many other forms of dynamo machines invented by Edison, such as the multipolar, the disk dynamo, and the armature with 2 windings, for substation distribution. Indeed, it is not possible within our limited space to present even a brief digest of Edison's great and comprehensive work on the dynamo electric machine, as embodied in his extensive experiments and in over 100 patents granted to him. We have therefore confined ourselves to the indication of a few salient and basic features, leaving it to the interested student to examine the patents and the technical literature of the long period of time over which Edison's labors were extended. Although he has not given any attention to the subject of generators for many years, an interesting instance of his incisive method for overcoming minor difficulties occurred while the present volumes were under preparation (1910). Carbon for commutator brushes had been superseded by graphite in some cases, the latter material being found much more advantageous electrically. Trouble developed, however, for the reason that while carbon was hard, and would wear away the mica insulation simultaneously with the copper, graphite, being softer, would wear away only the copper, leaving ridges of mica, and thus causing sparking through unequal contact. At this point Edison was asked to diagnose the trouble and provide a remedy. He suggested the cutting out of the mica pieces almost to the bottom, leaving the commutator bars separated by air spaces. This scheme was objected to on the ground that particles of graphite would fill these air spaces and cause a short circuit. His answer was that the air spaces constituted the value of his plan, as the particles of graphite falling into them would be thrown out by the action of centrifugal force as the commutator revolved. And thus it occurred as a matter of fact, and the trouble was remedied. This idea was subsequently adopted by a great manufacturer of generators. End of Appendix 10.